my name is Erini Lambrides, and I'm a PhD candidate at Johns Hopkins University, and I'm going to talk to you about obscured AGN, finding them and placing them in the context of galaxy evolution. And I'm going to be talking fast because I'm going to try to summarize 3 papers in 5 minutes. The Finding the Obscured AGN is about a study that we released earlier this year, and the placing them is 2 papers in prep that should be out on the archive soon. So, obscured AGN, they're growing supermassive black holes that are enshrouded by large quantities of gas and dust. And when you look at the X-ray background, AGN are a bulk contributor to the unresolved X-ray emission, and different X-ray background models predict different ratios of obscured to unobscured AGN. Despite the fact that there's different ratios in these different models, they all kind of agree that there is a large number of obscured AGN at many X-ray energies. Also, there's a lot of Compton thick AGN. So this is heavily obscured AGN. Now, obscured AGN are placed in the context of many different galaxy evolution models, in particular, the merging paradigm, which aims to explain how AGN get triggered in the first place, predict that obscured AGN should preferentially live in host galaxies that show signs of morphological disturbance after some sort of significant merger. And so we wanted to test that. The merger paradigm is contested in our field. There's conflicting evidence from either side of the aisle on that. And we wanted to start with the deepest X-ray survey to date, the Chandra Deep Field South 7 megasecond. It's centered on good south, so we have a lot of wavelengths to work with, which is great because AGN are a multi-wavelength phenomena. And so we cross-match everything. And one of the first things we find in paper 1 on finding these obscured AGN is that when you look at the intrinsic X-ray values from the catalog and compare it to another probe of AGN power rooted in the mid-infrared, the L Taurus star, we find that a third of our sample is 2 sigma below the expected relationship. Now, this sample is all of the AGN that are identified in the catalog in 7 megasecond south between the redshifts of 0.5 and 3. And in the paper, we take great pains to infer that we think that these obscured these AGN that have underestimated X-ray luminosities are obscured AGN, and that there is unaccounted for obscuration. And so when you include that obscuration and look at the space density as a function of redshift, we found something pretty exciting, which we're now able to constrain and probe a parameter space, which has been really difficult to probe before. So this is the lower luminosity, heavily obscured AGN parameter space. This is important because lower luminosity obscured AGN make up the bulk of obscured AGN, especially at these redshifts. Now, we want to take these galaxies and then do this morphological study and look at the merger state of their host galaxies. So we choose the most heavily obscured objects, the ones that have good HST coverage to make RGB images, take out the radio loud objects, and we're left with 66 radio quiet AGN. And before we can go on and just, run and look at the merger state of these galaxies, we needed to decide how are we going to determine the merger state of these galaxies. So when morphological studies are looking at galaxies at these redshifts, automated methods usually are quite difficult to use, especially since they may come with their own bias and systematics that you might not want to include for these higher redshift, very faint objects. So human classifiers are used very commonly in the field. It's kind of viewed as a necessary evil in some cases. And we wanted to know in paper 2, what was the reliability of human classifiers, and could we build a statistical model to encapsulate the potential bias a human might have when classifying a galaxy. And one of the really big takeaways that we got from this is that it is necessary to do this. It is necessary to try to constrain the accuracy of observers. Usually when someone is using humans to assess the morphology of a galaxy, they'll choose a control sample and a science sample. And let's say, if one of the humans in their study tends to see mergers everywhere and another one sees isolated galaxies everywhere, the assumption is that that bias is going to be evenly applied to their control sample and their science sample. And thus they'll look at the difference between the control and the science and make their results. We say that that is not that is not possible, that calculating and interpreting the merger fraction the usual way, so making that assumption and using binomial statistics, yields results that are dependent on the intrinsic merger fraction of each of those individual samples. And so we construct a Bayesian model which takes into account the accuracy of all of the set of human classifiers, and figures out the merger probability of not only an entire sample, but of an individual galaxy. And we run that on our sample of obscured AGN and a matched control sample in mass and in redshift. And we find no evidence of merger excess, no matter which way we slice and dice the sample. These are preliminary results. And summary. So paper 1, there's more obscured AGN than you think in Chandra 7 megaseconds south. We find 30% more obscured AGN than previously found when connecting the X-ray to other probes of AGN activity. Paper 2, purely methodology paper. So if you're a stats nerd about these things, definitely come talk to me. You can use humans in assessing merger state in galaxies, but you must constrain their bias or try to estimate their bias. And paper 3 is obscured AGN. The obscured AGN sample found from paper 1 are not preferentially found in mergers. Thank you, and I'm looking forward to some interesting questions.